Okay, so I had said that we were going to talk about some of the parasitic resistances having to deal with MOSFETs and all that kind of stuff, and I've made an executive decision to not cover that. That material really only presents itself if you're having to like make the active regions weird shapes in order to accommodate metal runs, and literally nothing we're going to do in this class would ever require that. So I'm avoiding talking about resistors for the 19th time, effectively. All right, I feel like I've beaten that topic to death. I feel like next year I'm going to try to orient things a little bit differently. I'm going to change it every damn time, and that's apparently a problem. But anyway, so we are on the topic of transistors in this IC class. So let's talk about two different ways that we can make transistors. All right. And this will bleed right in to my next topic, which we're going to cover today, which is matching in analog circuitry. All right, so laying out a transistor is pretty trivial in electric, right? You literally type in your width, probably leave the length alone, and let it do its thing. But there might be reasons why you want to split your transistor up into smaller parts. And that's literally the second part of this thing. What we're going to talk about is matching. So if we wanted to make a long length transistor, how might we go about doing that? So I guess let me explain by what I mean by that. So let's say that we have a transistor. Let's make it NMOS for the sake of argument. Here's our gate terminal. Here's our drain terminal. And here is our source terminal. And we to subdivide an aspect ratio of 10/8 into smaller transistors. And to make the math easier, let's make it 4 smaller transistors that we could string together in some combination, right? So what I'm saying is a single 10/8 aspect ratio transistor can be thought of as I'm changing the direction of this guy real quick just to make the picture a little easier to follow. Four transistors in series, where here's our gate connection, and this will be our overall drain connection. This will be our overall source connection, like so. So this would be in series with another 10/2, in series with a 10/2, in series with a 10/2, gives us a 10/8, all in all, okay? So if this were transistor M1, and this is purely just a labeling that I like to do so that I don't make dumb mistakes and stuff like that, so I'm going to talk you through it. I might call this guy M1A, this guy M1B, this guy M1C, and this guy M1D. So that when I'm looking at my overall schematic, where I probably didn't break it out into multiple capacitors, or excuse me, multiple transistors, I kind of know why I have so many more in my layout than I do in my schematic. Now, how would we actually lay this out? Anybody have any thoughts? So not really. That's a reasonable approach. It's definitely a reasonable thought as to why you might do that. Let me pull up electric for the sake of argument. Let's talk about things. Let me make a new cell. Series transistors. All right. So if we were to lay out series transistors, I'm just going to throw some N-type transistors here. I'm going to call this one M1A. And it's going to be a 10/2. And I'm going to make it 90. And I'm going to try to make that text a little larger so that you guys can see it. That's not how I do it, though. So I'm subdividing my transistor into 4 transistors, right? My original transistor. So I'm just going to drop 4 of these guys. In here. All right. So for my original transistor, what are the 3 terminals that I have access to? The gate, the source, and the drain of the overall thing. So I'm expecting to have access to the gate and the source and the drain of this overall configuration as well. So what I can do, instead of having some sort of weird serpentine type thing, which might work, I'm going to tie these active regions together. And then overlap them as much as I possibly can. So I'm not getting an error. I do get an error there. So let's tie that guy out like that. Bring this guy over. I hate how much this table is shaking. Okay, so error, no error. So that's as close as I can possibly make it. All right, so I've got all of them connected in series, where if the drain is my leftmost terminal over here for transistor M1A, then the source of M1A serves as the drain of M1B, etc. And these are all named absolutely ludicrously. So let me just change that to B. Like so. So I need to be able to send a signal to my drain or source. So I put a contact on one side. Since my transistor has a width of 10, I'm going to make my contacts 10 wide, wire it up, scooch it over until I get an error, and then move it one over until I don't. Do the exact same thing on the other side. Oops, not 510. That's bad news. That's way too many contacts. Make sure I select the right thing because it'll just randomly move stuff and make everything break. Connect those 2 active regions together, and now I can send a signal to the source and to the drain of my transistor. Effectively, you could string things together, but you're going to eat up a lot of space in doing that. And the idea of breaking these things in smaller parts is to make it physically smaller, right? Now, I need to tie all my gates together, so that's pretty easy. I can just literally tie them together and boom, it's done. Now the question might be, what happens if I just dropped, let's see, 10 by 8. Let's rotate it so that it's in the same direction. And then I put my contacts in and all that kind of stuff, right? Okay. Which one's physically smaller? The one on the right, the actual one that isn't made of a series connection, right? The problem here is that we can see process variations in the aspect ratio of our device. And this kind of weird interdigitated type thing here that we're seeing, where we've made it as 4 transistors in series, can be used in matching schemes to attempt to offset and overcome some of those process variations, where this guy absolutely cannot because it is a single device. Okay, so that's a series connection. It's easy enough. So that's how we make longer length transistors. Those bad boys in series. Now let's talk about long width transistors. Right. So let's say that we had a single transistor. We'll call it M1 again for the sake of argument. And it had an aspect ratio of 40/2. How can we make that 40/2 resistor? How can we split it up into smaller ones? And how does it need to be connected? Well, yeah, so if we want to be a longer length, we connect it in series. If we want it to be a longer width, we make the connection in parallel, right? So it would look something like this. And this is where we might wind up getting some of those serpentine-like patterns. To me, it's a little easier to see so there's our gate, here's our drain, here's our source. This transistor M1A has an aspect ratio of 10/2. M1B has an aspect ratio of 10/2. M1C has an aspect ratio of 10/2. M1D has an aspect ratio of 10/2, yielding an equivalent aspect ratio of 40/2. So let's go back to electric here. So we have our series guys up here. Let's start and active. No, and MOS. There we go. We tried to draw a 40/2 resistor here. And I'm going to rotate it so that all of my transistors are effectively facing the same direction. I'm going to need to scroll out some. It's trying to give me warnings, which may or may not matter. I guess technically, if I want to check my DRC to make things are all doing correctly, I should do that. All right, yeah. So that's a really long one. And then obviously we would have to put in our active regions and stuff for that guy as well. Oops. That's what happens when you don't select the right thing. It just randomly moves. Can be one closer. Yeah. So there's our 40/2 NMOS transistor. If we're connecting these guys in parallel, this is what I was getting at earlier, like this series combination up here, it makes sense, but for me, it's hard to wrap my brain around the fact that the drain of one transistor and the source of the other transistor are the same thing. Even though if I were connecting them in series, that's exactly what I should expect to see, right? So to me, drawing long width transistors makes a bit more sense because we do get those exact kind of serpentine patterns that you would really expect, right? So if I were to just throw one together real quick, rotate it by 90 degrees, make a couple of copies just to be lazy. I'm going to wind up using those active regions and connect those guys in between because I need to have access to every source and drain. Cancel, no, F5, not F6, there we go. And all right, so let me put my two active regions on the outside and then ask you guys which bits should be connected to what. 10, just 10. All right, so let's start with something easy. What would be the first thing that we would probably connect together if we were trying to tie all these guys together to be in parallel? Gates, right? Gates are very easy and well defined, so I would definitely say that that's a pretty reasonable place to start. All right, so all our gates are tied together. So what are the next connections that I need to make? Let's think about this, right? So would I tie, say, this guy right here that my mouse is over and this guy right here together ever? No, because that's effectively tying the source and the drain of the same transistor together, which means your VDS is always going to be 0, which means your current will always be 0. You're shorting it out. We can do that as a dummy type thing, which we'll talk about later on when we're talking about matching and all that kind of stuff. But if we're trying to make anything useful, that's a terrible idea, right? So what about this guy and this guy? Is that a source to source or drain to drain connection? Because I want my drains to be connected in parallel or all together and all my sources in parallel as well. Yeah, so I could come out, all right, so here's an issue. It's given me active region instead of metal. How would I go about fixing that? Because electric is crazy finicky. Like if I keep doing it, trying to select different portions of this guy, and I keep getting active, what could I do? I'm sure if you haven't had this frustrating bag of crap happen yet, you absolutely will pretty shortly. Thoughts? Vitaly, I think you were saying something, but I interrupted you once or twice. I apologize.
No, but, oh, yeah, you can.
So I could just go to pure and just drop some metal in there. Now, right now, the size of this metal by default is 3 by 3. And the metal that is surrounding my contacts has to be a minimum of 4 lambda in dimension, right? So I'm going to change this to be a 4 by 4 so that I don't get weird, funny looking things. And now from this metal layer, I can click here and it forces a connection, which is exactly what I want, because there's no way to connect metal to anything else when I have the metal layer selected, but it makes it 3 elements wide. So that's why it looks weird. So I need to go in here and fix it to 4. And what I like to do is turn off extension. And so when you start dealing with like big fat metal runs for your VDD line, your VDD bus and your ground lines, you'll see why it vastly oversizes things if you leave those extensions on. And I don't like my designs looking ugly. And then from here, where should I connect to? So what transistors should I be if we have? So this third metal connection, okay. And I'm going to move that up so that it makes it nice and neat. And because I am an insane person, I'm going to move that contact over so that everything stacks up nice and neat and I don't have random little bitty nodes all over the damn place. What's the next one? The very last one, right? All right, so let me hit F5 to do my design rule check. 0 error, 0 warnings. How close can I get this metal to the poly? Anybody have any ideas? Let's see what happens. All right. So I'm getting an error. Let's see what the error is. It has nothing to do with the polysilicon at all. It has to do with that other connected metal layer. I can run metal over poly all day long, not have any issues whatsoever. From a design rule standpoint, from a actual design of the chip or circuit or anything standpoint, why would that be a bad idea? Yeah, so parasitic capacitance, absolutely the correct answer, usually going to be the correct answer. So I would draw this something like this. And because I don't like this guy over here, being out weirdly like that, I drop it back in to where everything's nice and neat and everything's all kind of stacked up. All right, so ostensibly those are either all of my sources tied together or all my drains tied together. So what is possibly left? Yeah, the two things that aren't connected together need to be connected together, right? And now it selects the metal, no problem. Could not begin to tell you why. And then we can move this guy in. Yeah, 5. All right, so we have a wide width transistor that I would argue is maybe a little bit more compact than drawing it all in one go. And a long length transistor that is definitely not more compact than drawing it all in one go. All right, so that's how we can subdivide transistors into kind of smaller mini transistors to do some things. So let's talk about matching as it regards to analog component design. All right, and this is actually going to require writing both of our parts before we jump to the electric stuff. All right, so matching in analog components. So process variations during fabrication may limit accuracy and desired performance of analog circuits. So, anybody have any idea what I might mean by process variations? I'm assuming that you guys have been taking ELEN 437 or MSC 501 or whatever the hell it is. Anybody have any thoughts whatsoever on what a process variation might be? Yeah, so it could be due to if your etchant solution isn't completely homogeneous, right? So it's slightly more concentrated in one area of the chip than it is on another area of the chip. You're going to get slightly different etch rates. So that's going to give you a process variation. Slight misalignments in mask placement and all that kind of stuff are also going to be examples of process variations. Effectively, any non-ideality, like we design these things expecting an ideal behavior, in any non-ideality that crops itself up is either a mistake we made or probably more likely a process variation. Okay. So in an analog circuit, process variations can cause a significant problem. So I'm going to draw a circuit, and this is an impromptu pop quiz, not for a grade or anything like that, but I just want to see what you guys remember, if anything, from last spring. Ooh. All right, this is our circuit of interest, and we're not going to be analyzing this guy yet, but I would argue that other than this part right here, I should know what the hell I'm talking about. Okay. So what is this thing? Anybody got any thoughts? Actually, let me make it slightly easier on you. Let's say that this is the output. And these two pins are inputs. So you may not know what the whole thing is, but could you identify like different parts of it? I hope so. So for instance, what's this bit right here circled in purple? A what? Differential pair. Right. So for a differential pair to work correctly, what has to be true? This transistor, we'll call it M1, needs to be as identical as possible to transistor M2. Otherwise, it's not going to steer the current directly, which is the purpose of the differential pair. All right. What is down here that I've circled in green? A current mirror. What happens if this transistor M3 and this transistor M4 aren't matched? Right, so in this current mirror, we're assuming M3 and M4 are the same size. That means that the current that's provided by M3 shows up in M4, right? So we need to load this matched differential pair with a matched current mirror also in order to steer it properly. What about this whole top thing up here? It's also a current mirror, right? Current mirror, in this case, being biased by an ideal current source, which we know we don't have access to, so we would replace that with a transistor-based current source. So up at the top there, and I drew it, circled it in the same color because it's the same damn thing. We have a PMOS current mirror, where again, matching is absolutely integral. And down at the bottom, we have an NMOS current mirror, where matching is absolutely integral, right? So in an analog circuit like this, practically everything but this guy right here requires matching. What this guy right here is, well, specifically this guy is a compensation network, which is the thing effectively would have been, if 336 were 2 weeks longer, we would have covered that. It's probably going to be one of the first things we cover after we go through the review of transistor-based stuff here. So we have a current mirror biasing network on the left-hand side. We have a differential pair loaded with a current mirror, which is converting our double-ended output of our differential pair to a single-ended output. And then this guy, with the inclusion of this compensation resistor and compensation capacitor, form a common source amplifier. This is an op amp. This is a two-stage op amp, including the biasing circuit. This is what our goal in this class is to build. Whether we're going to do it using mostly PMOS or mostly NMOS, I haven't decided yet, but this is where we're going. By the end of the class, we should know how to correctly lay out, analyze, beat this thing to death. Okay. So let's say, just for the sake of argument, that I have a current mirror where I have some current IN flowing in. And transistor M1 has an aspect ratio of W/L. And then over here on the right-hand side portion of my current mirror, I have my output current, and M2 has a aspect ratio of 4 W/L. In the ideal case, what's my relationship between I out and I in? Anybody remember how a current mirror works? Yeah, 4 times greater, literally that simple, okay? But if we have process variations, right? So let's say that we split that transistor M2 up into 4 smaller parts. We might do that to make it a smaller size and all that kind of stuff, as we've seen. Tie all my gates together. They're all in parallel. Tie my drains together. I'm going to tie my sources together. So this is source, drain, source, drain, source, gate like so. Now let's say that there's a 1% increase in aspect ratio. 1% in W/L as we move to the right, meaning that transistor M2A has 1.01 with W/L as transistor M1 does. And transistor M2B has 1.02 times the aspect ratio of M1. Similarly, M2C has 1.03 times W/L, and M2D has 1.04 W/L. So that as we're moving from left to right in this chip, we have everything kind of spaced together nice and neat. every transistor we move over to the right, if they're all evenly spaced, we see a 1% increase in their aspect ratio. In this case, which is a bit exaggerated, 1% increase is a bit much. We would find that I out would be actually 4.1 IN, right? Because 1.01 plus 1.02 plus 1.03 plus 1.04 gives us 4.1. Okay. So this is where process variations can really bite us in the butt. These process variations, they don't only affect the physical quantities, although a change in the aspect ratio gives us a change in the drain current observed. So that's potentially pretty bad, right? But they can also affect things like threshold voltages and all that kind of good stuff, right? So when we need matched transistors, it is a big deal to figure out some way to mitigate the effects of these process variations. So there are two common ways to do it. Method number one is interdigitation. So let's say that we have two components. This could be a resistor, a capacitor, or a transistor. All of them can be split up. We'll call one component A and the other component B. And we split them into 4 smaller components, A1 through A4 and B1 through B4. Okay. A conventional layout might look something like this. So let's say that we have this box A1, next would be A2, then we have A3, and A4, and B1, B2, B3, and B4. And just to make our lives easier, I'm going to treat these guys as 2-terminal components. So I'm saying we're dealing with resistors and capacitors, but everything that we're dealing with here can be applied to 3-terminal devices like transistors as well. Okay. So if we tied these resistors together, these sub-resistors together, that whole thing between this terminal, let's call this RA plus, and this terminal here, RA minus, forms the resistance RA. And this guy right here will be RB plus, and we tie our resistor or capacitor together here. We would have RB minus like so. If we have that same 1% process variation, moving from left to right, and I'm saying this point right here, where our leftmost element is our origin. So it doesn't experience any process variation. Every element to the right gets 1%, right? Element A, I'm going to call it total, would be 0.25 times the nominal value of component A multiplied by 1.00 plus 1.01 plus 1.02 plus 1.03, okay? Which would look like 1.015A as its value, okay? So due to process variations, due to this 1% increase in quantity over this length, element A is now 1.5% larger than it was supposed to be. Element B would be 0.25A. I'm saying it's the value of A because we're trying to match it to element A, multiplied by 1.04 plus 1.05 plus 1.06 plus 1.07, right? And this comes out to be 1.055 times the value, the nominal value, right? So that's pretty crappy matching, okay? So what we can do to offset this, one means of making things a little bit better would be interdigitation, okay? So what interdigitation means is I could do this in a couple of ways here. So I'm going to draw my 8 sub-elements. And I'm going to say, I'm going to put A1 here, A2 here, then B1 here, B2 here, A3, A4, B3, and B4. Another thing that we could do, and we'll address it momentarily, actually, I'll just go ahead and put it down here. Why the heck not? So these are 2 different means of interdigitation. And when we only have 2 elements, it's practically the only 2 options. So we might have A1, B1, A2, B2, A3, B3, A4, B4, and then we have to wire them up appropriately, okay? But so interdigitation is literally what it sounds like. We split each thing into 4 different nodes and then we interdigitate them, right? We intersperse them together and then we have to, we will see that this results in an increase in matching, but a slight increase in the complexity of how things are wired up, right? So if we wired this guy up, for this guy, we would have A1 to A2, and then we have to jump over a couple to come down to A3 to A4, like so. And then a similar thing for B1 to B2. Jump over this guy. Right? And then down here, making my A resistor, I just connect all my A's to A's. And similarly, all my B's to B's. Like so. And what I wind up getting here, so for this one, my A total is going to be 1/4 of A times 1.00 plus 1.01 plus no 2, no 3, 1.04 plus 1.05. Total is going to be 0.25A times 1.02 plus 1.03 plus 1.06 plus 1.07. And what I wind up getting is 1.025 A here and 1.045 A here. So for this first one, where we've done it 2 A's and then 2 B's and then 2 A's and then 2 B's, right? It's better. It's more matched, or the values are closer to each other than in our completely unmatched state, but it's not as good as it could be. If we look down here at this other option where we're literally interdigitating every other thing, what we wind up getting is A total is equal to 0.25 times A times, let's see, so that'd be 1.00 plus 1.02 plus 1.04 plus 1.06, and then B total would be 0.25 times elements A's nominal value, 1.01 plus 1.03 plus 1.05 plus 1.07, giving us 1.030A and 1.040A. So the increase in the frequency of interdigitation here caused the matching to be better. So you might ask yourself, why did I bother showing you this 2 A's and then 2 B's, etc.? Well, you can do this every other thing easy peasy with resistors and capacitors. You'll find it much more difficult to do with a 3-terminal device like a transistor. That's why I introduced it. And if we go to electric here and I go to Explorer, this is what a AABB interdigitation scheme might look like. Okay. The AB scheme I didn't do because you can't smush the transistors together and make them look pretty in that scheme. So, all right, so not wildly difficult or anything like that. Does offer some degree of matching, but could be better. All right. So this is a quick and dirty way to do some matching for things that maybe aren't super critical. Now, let's talk about what's called a common centroid layout. All right, so let's look at this particular layout scheme. That guy went over, I'm gonna run out of space. So if I went A1, B1, B2, A2, A3, B3, B4, A4. I'm not going to worry about how these things are wired up for right now. All right. This is what's called a common centroid scheme. All right. So the reason why it's called a common centroid scheme, if we look at element A1 and element A4, they are kind of center of mass or center of gravity, if you want to call it that, would be this point right here in the middle, so that we have an A, which has no process variation associated with it, paired with an A that has the most amount of process variation centered with it. When we look at B1, it's paired with B4 so that they share that same point, or in this case, because it's linear, this axis of symmetry. The same thing for B2 and B3, and the same for A2 and A3. So that we group things together, so the least amount of process variation gets tied to the thing with the most amount of process variation. And when we figure out what the total contribution here is, so that would be 0.25, the value of A, 1.00 plus 1.01, 1.02, 1.03, plus 1.04, plus 1.07 gives us 1.035 A. And for our second element B here, we would have 1.01 plus 1.02 plus 1.05 plus 1.06, which also gives us exactly 0.035A. So a common centroid scheme gives us perfect matching. The downside of it is that it's much more difficult to wire up, right? We can extend a common centroid scheme like this into multiple dimensions. So instead of having a linear array, right? Because we've just made this thing really long. What we could do is we could make it one of either of these 4x2 arrays. And I'm going to walk you through both to kind of guide you as to how you would set one of these up, because I'm going to ask you to do it on your test. So if I put A1 here in the top left corner, I would need to compensate for it with A4 over here in the bottom right-hand corner, where I'm working on that middle point being the axis of symmetry, right? And then I could do the exact same thing for B1 here and B4 here, so that the point of symmetry between them overlaps. Then I could do B2 here, B3 here, giving me A2 here, and A here. And it's fairly easy to see that we have our common centroid. So we literally just, hopefully we can all see that for this 4x2 system, we want that point there in the middle to be everything where everything is balanced, right? So we could also do A1 to A4, A2 to A3, B1, B4, B2, B3. This also satisfies the common centroid configuration, right? Because A1 matched with A4, B1 is matched with B4, A2 is matched with A3, B2 is matched with B3. These are the only two options when we have a 2-element 4x2 set. We could subdivide it into 8 and we could make a 4x4 grid. I mean, there's an infinite number of permutations that we could do, but I want you guys to understand how common centroid works versus how it doesn't. So for instance, just this will be the last thing if we had something like this. Is this common centroid? See, it's tricky. Logan, what are your thoughts? I'll pick on you since you're back over there in the corner.
Well, the top ones are meant for A's to A's. And I'll say
So there's a couple of ways that we could think about this, but the short answer is that it, as a unit in and of itself, it isn't common centroid. And so what I mean by that is if we have this 8x2, or excuse me, 4x2 grid, the expectation is that our lines of symmetry are going to be like this. So we have an A in the top left, but we don't have an A in the bottom right. But what is interesting about this particular grid, this is what you would consider, I think it's called tiling. You have a 4-element system with a common centroid here and a 4-element system with a common centroid here, or you have a 4-element system with a common centroid on top and a 4-element linear system with a common centroid on bottom. So it can be subdivided into numerous smaller common centroid designs, but the total thing does not satisfy the requirements, okay? So tiling is another thing that can be done as a kind of it might make things a little bit easier to route. So it's kind of an intermediate place between interdigitation and a true full-on common centroid thing. But yeah. Yes. A2 and A3. So the number is entirely irrelevant. It's just that it's a part of element A. So element A is subdivided into 4 identical parts. So it really doesn't matter that it's A1 matching with A4. It's an A element matching with an A element, which is what I did here, right?
Oh, okay.
Right? So I'm saying this A does not match, this A in the top left does not match with this B in the bottom right. Therefore, it cannot be common centroid.
Okay.
But if I were ignoring everything to the right, this A in the top left corner matches with the A in the bottom right, the B in the bottom left matches with the B in the top right. So everything over here is common centroid with respect to this point. Or if I look at just this top row, this A on the left side matches with the A on the right. The B in the left middle matches with the B on the right middle. So we have common centroid about this point and so forth.
Okay.
So yeah, so the 1s, 2s, 3s, and 4s are just so that I have exactly 4 identical parts of element A and exactly 4 identical parts of element B. But where they're positioned does not matter. So this being A1 doesn't matter. It being part of element A does.
Yeah.
All right, I think that's enough out of me for today. So just to remind you all, we will not be having class on Friday because I have the Industrial Advisory Board meeting stuff all day for the overwhelming majority of you. And so that means I think everyone but Albert, because Desmond didn't show up. We do have that IAB meeting for the senior design students Friday afternoon that you are expected to show up to. If you are a member of IEEE or Eta Kappa Nu, you may have been contacted to come visit with the board and all that kind of stuff. There's nothing preventing students who aren't members of those organizations from coming either. If you want to sit through a 4-hour meeting where we go over the minutes from last year and all that kind of crap, whatever. talk about what we're gonna be doing to upgrade the power lab, all that kind of good stuff. We try to have a couple of students there. Honestly, I'm not sure why, but I've been told that I was supposed to have students there, so I have students there. With regard to the lab tomorrow, I probably have another conference call, but I'll just be in my office to take it at some point. I have gotten all of you access to this, to room 202, the senior design lab and all that kind of stuff. So you should be able to just swipe in with your card as of a couple of minutes before this class started, so that you can go in there and start messing around with crap at your leisure. All right, see you guys later.